A very good morning and a warm welcome. Once again, welcome you all on this another YouTube live organized by Nehru Planetarium. Whenever we talk about universe, we all get mesmerized by its beauty. Universe is different for all of us. So today we will be talking about how universe keeps giving us surprises. Understanding the origin of the universe is one of the oldest human dream, but only recent has entered the realm of Science. Our technological capabilities have advanced to another some of the fundamental questions of the universe. In the last few decades, astronomers have for the first time identified the universe's primary components. Unexpectedly, the universe differs significantly from what we believe only a few decades ago. These suggest that more surprises may be in the store. To talk more on this topic, we have with us Professor S. Shankaranarayanan, Institute Chair Professor of Physics, Department of Physics, IIT Bombay, which is known as Mumbai nowadays. Planetarium welcome you, sir, for agreeing to talk on this with us. Professor Shankaranarayanan obtained his PhD from the Inter-University Center for Astronomy and Astrophysics, popularly known as IUCA Pune. After postdoctoral work at ICTP, Triest and Albert Einstein Institute, Germany, he was at Marie Curie Fellow at the Institute of
Christ and Albert
Cosmology
Einstein
and
Institute,
Gravitation, Portsmouth between 2009 2017. He was a faculty member in IISER Trivandrum. He joined the Department of Physics, IIT Bombay in July 2017, where he is a chair professor. His area of research are black holes, physics, early universe cosmology, modified gravity, and quantum gravity. It's a great privilege to host you, sir, at the planetarium, and we all are really excited to explore this topic with you. So, over to you.
Thank you very much. I'd like to thank Nehru Planetarium for inviting me to give a talk. Can I share the screen? Is it?
Yeah, yeah. So, you need to share it again. I think we lost
I have
that.
to share it again. Okay. You can see the screen now.
Yes, we can see.
Okay. So today I thought I will give a brief history of how, as humans, we have been able to understand the universe and how our perception of the universe has keeps changing because because of the observations, and also primarily because we as humans will not be able to understand the universe completely. So that is how I have. That's the reason why I have put the title as "The Universe Keeps Giving Us Surprises." The universe is not surprising us, but we are getting surprised because of the fact that our own perception is different all the time. So to set the stage, I have started given you a diagram here, which is basically which all of us have heard. This is a parable of the six blind men and the elephant. This is an old Indian story, and it was popularized to the West by John Sachs. So there are several versions of the story, but all the versions are actually have drives one thing, which is basically is that the perception is subjective if we measure only a part. So let us just go through the story once, so that then you will all understand what I am actually heading to. So there were six blind men in a village, and in the village there was an elephant which was there passing by, and all the villagers were very excited to see it. But these six blind men were not cannot see, obviously. So what they decided is, okay, instead of they seeing the elephant, they will go. Each of them will go and touch and feel the elephant. So what they did is each of them actually looked at each part of the elephant, and they were happy. And then they came back, and then each of them were explaining to each other what their perception of the elephant was. One person said it's a giant wall. One person said it's a rope. One person said it's a giant tree. One person said it's like a snake. one person said it's a huge sphere, and one person said it's a fan. Okay. And so of course they never agreed on each other. So of course they were on a heated debate. And then what happened is there is a sage who passed by, and the sage uh, stopped all of them, and they said, all of them are right and all of them are wrong. So he said that is because you have only seen part of the elephant, you have actually not seen the entire elephant. Now you replace this, actually can be extended to cosmology, or even actually to any subject for the matter. So you replace elephant with universe and blind men with us, and you the elephant itself is and the observations are basically what we make. Fine. So the sage is observations. So basically, what is the current state is that we are all heating. A lot of us cosmologists and physicists are all fighting with each other, because each of us think that the universe is composed of something else, and we all think that other person is wrong. So this is where the status is. So now we'll go back in time, and then we will now think about how did we come about this. Fine. Okay. So to give an idea, I have been given this picture, which is now the famous picture of from the NASA, which talks about our current understanding of the universe. Now, I have also given on the left side of how our history of our perception of the universe has changed. So I have divided this into 5 epochs. It could be very different also for others, but I have just felt that this kind of as a number which is useful. Also, it is also gives a perception of how our understanding has changed. So I'm going to go step by step, and what I was planning to do, just what I mentioned to the person as well, that I will at every two divisions I will take a pause for 2 minutes. If people have any doubts, they can even ask questions. So the first epoch is basically starting from the early humans till 1500 AD, where everybody confidently thought that we are on a geocentric model, and everybody thought that we are at the center of the universe and everything else revolves around us, which kind of natural. And then we moved from the geocentric to the heliocentric, and Copernicus was the main person, and he had revolutionized the understanding of heliocentric model. But still, this model has a lot of explanations and understanding of how the planets are moving around the sun and everything else. But of course, it doesn't answer one of the most important questions, which was basically referred to as the Olbers paradox. This was a paradox for almost like 100 years, until Hubble expansion and general theory of relativity came in. And so that's where the fourth epoch is, which is what we call it as the Hubble expansion and the Big Bang. And till 1997, 98, everybody thought that we have understood the universe and we know everything about it. And at some in the observations again said that no, we are almost completely off. And this is what we call it as the dark ages, or the dark energy epoch, or the accelerated epoch, and that is what we are currently in. So I will quickly go through the first three as soon as possible, and then we will go slowly one by one. Fine. So this is what we have been seeing the universe from time immemorial. So we see lots of stars, and we group them into various clusters, and then we see them that this is how we refer to many of these things. Fine. Now, and this is what people observed it, and people thought that we are at the center, and everything around us is actually moving, and that is what Greek philosophers, starting from Aristotle, um, said that. And this was actually nurtured by Aristotle, and then it was popularized by Ptolemy. So, and it is what is referred to as a geocentric model. Geo means Earth, so Earth is at the center. Everything, even sun, everything is actually revolving around us. This is what people thought, and then this is how, and they of course didn't think about universe as what we currently think, but they also think that this is all stars are all hanging around here somewhere. They never bothered about it, but their main aim was to understand the motion, because please understand, astronomy was very interlinked to agriculture. If you don't make predictions about the various this thing, then various patterns, then the farmers will have problems with the famine and things like that. So astronomy was forefront, is because of the fact that it was very well linked to the agriculture and farming. Fine. So basically, all the celestial. So the idea was that we are at the center, and everything else is moving, and all the celestial bodies move around it in a perfect circle. But however, the problem with this model was that there's an issue of this retrograde motion of Mars, which I will show it in the next slide, and which the geocentric model couldn't explain, at least the initial model. So basically, this is the pattern of Mars. Now, as you can see, suddenly it moves back and comes back. Okay. Now, so if you have a geocentric model, then this cannot. If you have a heliocentric model, which is what I will explain it later, this is very natural. So it will come back as a natural explanation. But in the geocentric model, you have to explain this. So what Ptolemy said is that, okay, so he said that, okay, so if Earth is at the center, then how do we explain this? So he came up with this, what is called the epicycle theory. The epicycle theory is a theory which basically tells us, it's like how our earlier clocks used to work. So you have a wheel and there is another wheel. So basically there is a little wheel and a small and a bigger wheel, and the small wheel is actually going around in this. So basically there is a big wheel here and there is a small wheel. Fine. So so this big wheel is the planets and others are actually going around the big wheel, and then they are also going around itself. Okay. So what he was able to do it is that once you if you go around like this, then automatically this can explain this motion, or the epicycle motion of the retrograde motion of Mars. But however, the problem was that if you use the epicycle theory, then it cannot explain. It can only explain it. The motion of moon cannot be explained, and more importantly, it will alter the. It will say that the moon size should be different at different times, and we know that all through the year it looks the same. So this was one of the problems of the epicycle theory. Fine. So of course, so people have wondering about it, but people didn't want to move away from the geocentric because they were thinking that the Earth is at the center, so everything else is around that. So, but Copernicus was a Polish astronomer. He thought that there is a serious problem with the geocentric approach, because he said that because we have various issues with the observations of Moon, for Mars and other things. So he said, okay, so he said that the other way of thinking about it is basically you make Sun to be the center. So that's where Helios means sun. So sun is at the center of the solar system, and then he was trying to look at how, using this, he was trying to explain how the different planets are in the solar system, and that seems to be even now correct, because we know that we are sun is at the center, Mercury, Venus, Earth, and the most moon is actually going around the Earth, and then Mars, Jupiter, and so on, and that we know that it is correct. So this is for the first time, by very clearly he was able to put together a few things, and he was put together physics, mathematics, and astronomy came together. That was the first period, around 1540. Okay, but the problem with the heliocentric is that there was not much data available that time, and and although he had a theory, but he couldn't confirm it basically, or he had a model, he couldn't confirm it because there was no much data available. Please remember, this was before Galileo, when the telescopes were not invented, so there were not much of data itself available. But Tycho Brahe, who was an astronomer. Basically, he was a Dutch astronomer. So he was basically, what he was doing is, in his spare time at night, he was measuring all the planets, and he was marking them on his sheet, and very very systematic observations of all planets and various stars and things like that. So what I've shown here is basically only one, which is observation of Mars from 1582 to 1600. So he was basically doing it for like 20 years. and all his observations were. Okay, but why was Tycho Brahe doing it? Because Tycho Brahe was actually had a very different model of that universe that time, or what we now refer to as a solar system. So he believed an intermediate system where Earth is fixed, but Sun goes around the Earth. Okay, and other things. Basically, there were other planets were actually going around. So that's how he believed it. Okay, but he couldn't have any clear picture from his vast amount of data. He actually couldn't do much. So please remember, this was 20 years of data. Now, what I have basically plotted here is also the data, the current data, and how it fits the masses observation with the current Kepler laws. And so basically, Kepler, what he did was Kepler used Tycho Brahe's data, and he proposed the laws of planetary motion. So these are basically the laws of Kepler's. Now we can use the Newton's theory. We were able to now see that we can use the theory and we can fit the data very well. Okay, so what basically Tycho Brahe data was useful, and Kepler used the Tycho Brahe data after his death, and he proved the heliocentric model of the solar system. And he developed what is now referred to as the three laws. I will not get into the details of the laws, but basically the three laws tells us that first tells you that it is basically if I have a massive object like Sun, then a planet like Earth moves around in an elliptical orbit. And if I have a line joining a planet and the Sun sweeps an equal area during equal intervals of time, and the square of the orbital period of the planet is directly proportional to the cube of this. So this I just wanted to put it for completeness, but this equation laws are really not relevant for what I'm going to talk. But that's where Kepler's law was just a law, but actually Newton's proposed the laws of gravitation, and he combined it with Newton's second laws of motion, and he could actually get all the three laws, especially the second law and the third law. Fine. He could also derive the first law, basically why elliptical orbits are there, from the Newton's laws of gravitation. So that's where things were. So that was really peak, like for instance, by 1700 and 1800s, everybody thought that we have understood the model of the universe. I can take a pause if there is any question. I can just take a pause for a minute and then I can move on.
So till now, if you have any kind of a doubt related to the presentation we are talking about, please feel free to drop it in the chat. I can certainly take that question and sir can answer that. If you have anything till now, which point you didn't understand or you want more clarity on that, feel free to ask that. We'll be taking a pause.
Okay, I think I can move on.
Yeah.
Okay, fine. So now I'm moving on to the third epoch, as I pointed out in the earlier slide, what is referred to as what I'm referring to as an Olbers paradox. So basically, Olber in 1823 asked this, what people must have thought was a stupid question: why is the night sky dark? So according to him, if you use the Newton's theory of gravitation and whatever we have understood that time, then according to him, actually this should not be the way the night sky should look, but it should actually be much more brighter than the during the day. So let us just go ahead and look at why. And of course, everybody laughed at it that time. But actually, that's where it was kept in. People didn't understand the paradox, and it was called a paradox for 100 years. But now, of course, we know that paradox is no more. So let us just go about in understanding what that Olbers argument is. So let us now, to understand this, I'm going to consider a light, candles. So I have two sets of candles. One set of candle which is close to us, and the other set is little far away from in the room. So these are the two. Now, the two candles, set of candles, emit the same amount of light because they have the same the same amount of flame in there. But this set of candles apparently looks dimmer compared to this. Right? This is the everyday experience we see. Like for instance, if I shine a light, if a light comes and hits you from very close by, for instance from a car, you want to close your eyes, but if it is very far away, you can in principle see it. It's the same thing even with sun, for instance, during the day, right? Fine. So basically, the candle, we call it as a candle. So in astronomy and astrophysics, we define what is called a luminosity, which is the energy. It emits certain amount of energy per unit time. So that is what we call it as a luminosity. Now, the candle, if you move the candle away, this candle should appear dimmer. And the way we understand it in astrophysics and astronomy, even in physics, is basically flux, which is called as flux, which is luminosity per unit area, per unit solid angle. So basically, if it emits in all the 360, in all the direction, in all the full direction, entire 3 dimensions, so it will basically be, we can divide it by 4 pi d squared, where d is the distance from the object. So that is the reason why this appears brighter compared to this. That's what we define. Okay. So now let us ask a question: how did Albert make this? What are the assumptions he made in order to make this paradox? What was referred to as a paradox? So what he said is that, okay, let us say we are at Earth, and we are only receiving light from all stars and galaxies. At that time, we didn't know much about other galaxies, but anyway, so we can measure all these galaxies. Okay. So he assumed that the universe is static and infinite. Basically, that is what we know that time. It was 1800. So everybody thought that universe was static and it infinite. Basically, it was infinite distance, and infinity itself was not well defined. But we assume that it is infinite. So what does infinity mean? So we should be, if it is infinite, we should be able to see a star in any direction, even if it is far away. That is because that time people didn't know that there is a speed of light. So there is essentially a maximum speed of light that also was not there. So in that sense, he said that I should be able to see every part of the universe, however infinite it is, we should be able to see. Static basically means that the distance should have a similar brightness as the sun. So basically what it says is that I should be able to, if it is static, so I should, given this, I have a sun here, the distance is roughly which I know, for instance, then all these I will be able to calculate what are the total brightness which we will be able to receive. This is what we receive. Okay, so now if you make this assumption, now let us look at how will the night sky look. Now this is sun, so we will have all stars. So if you take the Olbers paradox and you assume whatever he did, so he made a very clear picture. Say that this is because if you have assumed the universe is infinite and static, then your night sky should not look like what we are seeing right now, but it should actually be even more bright. So please remember, this is sun. I'm going to put the video again. So this is sun, and these are different stars and galaxies and things like that. And so what he said is that this light, diffuse light, which you should see, it actually should be very bright. So so we don't see sun at night, but so this will not see, but in the night you should see a very not a sparse light, but you should actually see a full light. So you should actually be daylight all through. That's what he basically said. So of course we don't see this. So in that sense, almost assumptions was maybe wrong, but with the assumption, whatever prediction he made was actually correct. But that was inconsistent to what we have been seeing all through the centuries, saying that our night sky is actually very dark. It should actually be not bright, right? So what I want to now look at is, now that's where I'm going to make a deviation. So now let us relax one assumption which Albers made, and let us see what the consequences are. So let us assume that the universe is actually expanding. So when I say it is expanding, which basically means that, please remember this, you go back to this simple equation. If the universe was expanding, so this basically means the distance d between the observer and between the sky, between the galaxy or the star and us, it is going to change. So if this is d is going to change, then that change with time. So this is going to be increasing with time. So basically, this flux we will see is going to be dimmer and dimmer. That's basically the assumption. So we are relaxing the assumption which Albert made. We say that the universe is expanding, which implies that the universe will receive less light from the distant stars. But then the interesting consequence of it is that if you now let us now play the video backward. That's what I've done here. So if I go back, so now I'll go back in time. So then the universe should have been smaller in size. Then it should have been, even if I go further in time, it should have been smaller in size. If I go further in time, I'll go further smaller and smaller and smaller. So if I go further and further back in time, then if the universe was expanding, is expanding right now, it should have been expanding before, and it should have been actually a universe should have been a finite. So basically, the only assumption which I'm going to say is that if you relax, so Albert made two assumptions. One is that it is static and it is universal. So let us not assume that it is static. I'm saying that it is actually it is expanding, for instance. Then automatically, the fact that it is expanding right now, it tells you that it should have been smaller in size before. Back and back, keep on going back. It should have been smaller and smaller size as we go back in time. So it should have been it should have started with a small region. So basically, if you relax one of the assumption of Olbers, which is the universe is static, so which treat it as a universe is expanding, then automatically another consequence of this is that universe is to be finite. So basically, the distant light has not reached us still. So what it basically tells us that both the assumptions which Olber made, although it seemed to be correct that time, but in the current understanding, it will tell that we are actually it may not be correct. So, but interesting thing is, if you relax one of the assumptions, the other assumption automatically tells that it is wrong. Fine. So you will one assumption which we just say that we relax it, then the other assumption automatically tells that it is actually fine. Good. So now, what is the consequence? The consequence is that what we keep looking at. It's called the Doppler effect. So I'm going to explain this from what we know. So we have this everyday experience when there is an ambulance or a fire alarm which is coming. When it comes to us, it appears to be of higher frequency, but if it goes away from us, it appears to be of lower frequency, and that is what is referred to as a Doppler effect. So I will explain this a little thing, because that is very crucial for cosmology. And so what is Doppler effect? It is basically a shift in the frequency of the sound waves due to non-zero relative velocity between the source and the observer. If the source and the observer have two different velocities, then the frequency will be different. So if there is a delta mu, which is a change in the frequency, is proportional to the change in the difference between the velocity. If the difference with the velocity is zero, then there is the delta nu is zero, and the frequency of the source and the observer will be identical. So let us just pictorially understand. So let us take the case we are observers somewhere here. The source is stationary. What is happening is that the source is actually emitting a circular light, a circular wave, and the sound waves are propagating isotropically at all directions and at the same speed v sound. So the distance between the wave fronts is the wavelength, because that is what we refer to as wavelength, and the frequency is the same for all observers. Now let us take the interesting thing. Let us take the case the source is moving towards the right. So if the source is moving towards the right, now what is happening is that the distance between the wavefronts, I'll just repeat it again, the distance between the wavefronts are shorter, while the distance between the wavefront for the observer behind is actually larger. So what it basically means is that the wavelength for the observer who's here is going to be smaller, but the wavelength for this observer is going to be larger, which implies, because we know that the frequency and the wavelength are inversely proportional, which implies that this observer will see a higher frequency. That is the reason when the ambulance comes close to us with a very high speed, there is a shift in the frequency, and that is the reason why we hear it. It's a deafening frequency. But if it goes away, which is going away from us, so the frequency is coming, it's going slower. Hence, we don't it doesn't irritate us. So this is the principle of the ambulance, because the reason why the ambulance is doing is because it has to irritate us and we have to move away from it. We don't want to disturb them. Okay. So so now I have so where is the Doppler effect coming in? So this is where the interesting thing comes in. So the same thing, what we call it as a Doppler effect, can be actually seen. So let us take the case. I have a star or a galaxy now, and we are here. Now they are emitting electromagnetic light at different frequencies. So we see them emitting it, and let us take the case that if we emit them, let us take we have a galaxy which is close by, and we measure the their properties using a spectrogram, and we see that this is the same. Now we see another galaxy, which is, let us take another galaxy which is far away or something. Now what you see is, if it is the same kind of galaxy, then it should be emitting the same kind of frequencies and this thing. But what if they emit a different frequency? If all of them are actually very different from the what you actually expect, then we can figure it out that these galaxies are actually moving away from us. So basically what we are trying to say is that if the same principle which we use for the ambulance and the fire alarm can be used in the cosmological context, and we can understand what, from this we can able to understand what is happening in the universe. So basically you take two galaxies, galaxy 1 and galaxy 2. Galaxy 1 and galaxy 2 should be something similar, which we can assume to be true, because there are lots of galaxies now, so we can assume this to be true. And take one galaxy which is close to us, take one galaxy which is very far away, and then observe the spectroscopic pattern, the image, like an ECG image which you see it. So now it's electromagnetic signal which you see it. Now you see this and compare it with this. If the shift in the frequency is same for all of it, all the in the frequency band, then this basically means that this is actually going away from us. And if it is blue shifted, then it is actually coming close to us. So basically this is what is called the cosmological redshift. Basically redshift basically means that the emitted frequency and the observed frequency are very different, and the frequency of the emitted and observed, if it is opposite, which basically means emitted is greater than observed, then it is Z is positive, which basically means redshift is positive. If the emitted is less than this, then it will be negative, which basically means it's coming towards us. So if Z is positive, it is going away from us. If Z is negative, it is actually going towards us, coming towards us. Okay. So this is what actually Hubble did from 1920 to 1930, roughly for 10 years. He basically did this. He observed galaxies which are far away from us, and he measured the spectroscope, measured them using a spectrometer, and then analyzed what these galaxies are actually doing. Fine. So this is Hubble. So basically he had a telescope. He just went on measuring it for 10 years basically. And this is the plot of what he did for 10 years. So basically this is what was published in 1929. And so what he did was, he basically measured two things. He got two things. One is basically he got the distance, and the second one is the velocity. So for every galaxy, he was measuring the distance, he was measuring the velocities. So, and then what he did is, he just plotted as a function of, so we defined the distances are large in astrophysics. We defined what is called a parsec. So parsec is 3.26 the light year times, and megaparsec means 10 to the power of 6 times parsec. Okay. So roughly it is 10 to the power of 24 meters. Okay. So it's this is the distance of megaparsec, and this is in the velocity kilometers per second. It's not meters per second, but it is kilometers per second. Astronomical objects actually travel very, very fast, so we are measuring them. So what he did is, he plotted all these galaxies, whatever he could measure, and he plotted them in this plot of velocity versus distance. So of course he was not, as of course his measurements had a lot of systematic and instrumental errors. So, but then what he said is he said that he will make a simplest of assumptions, saying that this velocity is actually proportional to distance, and this is what is referred to as the Hubble's law. So he basically said that velocity of the galaxy is proportional to the distance, and the proportionality constant is now referred to as the Hubble constant. Now, this was the measurement he did in 1929, and this is the measurement for which I'm going to discuss this plot again. And this is the plot, sorry, and this is the plot of velocity of distance. This is by Rees et al. In 1999. This is 70 years difference. Now they have measured for a much larger distance. Please remember this is in 2 megaparsec, and now we have gone up to 400, now even more than that, now in the last 23 years. So they have gone even beyond this, and you can see that this profile is fitting with what the Hubble's law predicts, which is V is proportional to R, where proportionality constant is Hc. So basically, what I wanted to, what the important thing which you have to mention is that Hubble did this for 10 years. Of course, that time the technology was not very good, but with that technology, he was able to, whatever he could measure, he made a bold interpretation. The interpretation is that the velocity of the galaxy is proportional to the distance. So it is going away from us. That's basically what is the most important. If there is any question, I can just pause it here and then I can take the next one. I can move to the next slide.
Um, so one question is from Siddharth Narayan. He really wanted to know the Epoch 2 because he mentioned soon after your presentation. I did not understand Epoch 2.
What 2?
I think in the chronology you mentioned this, like Epoch, E-P-O-C.
Epoch 2. Epoch 2. Hello?
Yeah, yes, sir.
Yeah, Epoch 2. He didn't understand Epoch 2?
Yes. He need more clarification on this.
Okay, so Epoch 2 is basically going from, so let's take this picture. This was Epoch 1, where Earth was at the center and everything is moving around us, including Sun. Okay, this is what is called the geocentric system of solar system. Okay, or geocentric system. Basically, Earth is at the center and everything is moving around us. The heliocentric system is basically what the Copernicus predicted, which is basically Sun is at the center and everything is moving. So this is Epoch 1 and this is Epoch 2 of our understanding. When I say Epoch 1, it's not that the universe is changing. It is just that our understanding or the perception of the universe. Okay, fine. Any other question?
No, sir. I think, Siddharth, you got your clarification. This is what you wanted to know. If not, please mention it. We'll take it later.
Okay, good. So now, so this is basically the starting of the understanding of the universe. So basically what Hubble said is that our universe is actually expanding, and the farther the galaxy is, farther it is going away from us. That's basically what he said. Fine. Okay. So how do we understand this? So basically, so the Hubble's law tells us that the universe is not static. But the problem with this is that the Newton's theory, like electrostatics, is a static theory, and it is described by what is called the Newtonian potential. Now, also, let us now calculate if I have two galaxies which are separated by a distance. Okay, and if you want to calculate, so the speed is like a 0.2 times the c. C is the speed of light. So it is basically, it's a very high speeds. So we know that at very high speeds, the Newtonian theory fails. We should replace them with some other theory. And now we know that theory already that was existed, which is the Einstein general theory of relativity. I'm not going to discuss that because that itself is a big topic. So we are not going to discuss that. So only thing which I'm going to say is that to understand the Hubble's law, we cannot use the Newtonian theory of gravitation to explain it. We need something even better, which is general theory of relativity. The Newton theory of gravity is very good to understand solar system experiments, most of it. Okay, Now, of course, we there were some small error this thing which was again clarified by the Einstein's theory of relativity. But to explain the in the cosmological context, we have to abandon Newton's theory of gravity, and we have to go to general theory of relativity. And the interesting thing is the general theory of relativity naturally explains the expanding universe. So the epoch 4 is basically where we are right now, in the sense we were there, where the universe is actually homogeneous and isotropic. Fine. So what Friedman, Lemaître, Robertson, Walker, these are the four people who came up with this model of the universe. So they made a very simple assumption that the universe is homogeneous and isotropic. Homogeneous means there is no preferred observer position, which basically means that all observers in the universe will look at the universe like in the same way. Isotropic means all direction for all observers looks the same. Fine. So is this assumption true? So this is basically a map of the universe by SDSS, Sloan Digital Sky Survey, where they have actually mapped millions of galaxies. So they can't see it in this region. That's where it is black. But other than that, this region is all completely mapped. We know the distance of the galaxies. We know what the intensity, everything about it. And they have mapped the entire universe using this. Now, as you can see, if you look at it in the largest scales, it's like when you take a Google map and you zoom out, everything looks homogeneous to you. So that's where it is. In a largest scale, it looks homogeneous. But when you go into this granular scale, then of course there will be it doesn't look homogeneous. But so that is basically what the assumption which Friedman, Lemaître, Robertson, Walker made, saying that we assume it's homogeneous and isotropic because they did it because it is the simplest possible. But now we know that assumption is actually true because from the observations we know that each in the largest possible scale the universe looks homogeneous. So given this, so this is how the line element look. I'm not going to explain this, but if people are interested, I can come back to it later. So now, what are the predictions of this Friedman-Robertson? So naturally, as I mentioned before, it can explain the Hubble's law, which again tells you that if I go backward in time, if the universe is expanding now, if I go back in time, then of course it is going to be shrinking and shrinking. So it is going to go back and back and back. So it has to go back, and it is going to become a very small, and that is what we call it as the epoch is called as Big Bang, and that Big Bang we don't understand well. So the Friedman-Robertson-Walker model of the universe explains the Hubble's law. It also explains the observations which we see in the Sloan Digital Sky Survey, which basically tells you that the universe is homogeneous, and these are the galaxies which we see. So all of them are actually clear. Now, what is the physical consequence? Now, the physical consequence, which again we can only do it because of general theory of relativity, it tells you that if the temperature of the universe was, now we know that it is approximately 3 Kelvin. If you go back in time, the temperature will keep increasing, and this temperature will increase with the scale factor, which is what I mentioned in the previous slide, which is a scale factor, which tells you how fast we are expanding. Okay, so the temperature of the universe will increase with the scale factor as we go back in time. So currently it is roughly 3 Kelvin, but if you go back in time, the temperature will go up to very large, and at the Big Bang, it is it's infinite almost. Fine. That's where we don't understand the temperature close to the Big Bang, but we understand after that very well. Okay, within a second of Big Bang, we understand it very well. So what is the consequence of the temperature is very high? Because then what happens is that, as you can see, this is a proton and this is an electron which is going around. Now, if you go back in time, this temperature, because of the fact that these are very high temperatures and the photons, which are basically very high energetic photon, these photons will come and hit the electron, and the electron will go away, and now there will be only ions which will be present. So it will be just a proton. So what happens is that when we go back in time at the early universe, there was no proton, there were no heavy nuclei, there was nothing. There was only protons, electrons, and photons. So they were all moving at very, very fast speed, close to the speed of light. Everything was going very fast. And as the temperature cooled down, like when the universe is expanding, then this proton and radiation, electrons, everything cooled down, then the proton and electron, because they want to be electrically neutral, they became hydrogen, and then other higher elements started forming. So the one of the interesting consequences of the Friedmann-Robertson-Walker metric, now the model, is that as we go back in time, the temperature increases. Since the temperature increases, it will these electrons, protons, they will be ions, and they will be in a constant interaction with photons. That's basically what was the interesting, important consequence. So this is basically the plot of by Peoples in 1964, and for which he was awarded the Nobel Prize in 2019. So in 1964-65, he basically predicted how the universe. This is the reason why he said possible thermal history of the universe. So he basically predicted how the universe is evolved, starting from a very small, early time and the late time, and how the universe was evolving. And of course, this prediction was consistent with what that time is, but now we know that we are not in the current time, which is this is an issue. I'll come back to it when I'm discussing. So basically, what he said is that when the universe was hot, everything was at equilibrium. Proton, electrons, radiation are all living together. But once it cooled down, then they were all decoupled, and what is referred to as the last scattering surface. And that is the first light which we see, which is the cosmic microwave background we see. I'll come back to it in a minute. And the temperature we see, and then everything else cools down, and this is how the evolution of the universe is. So I'm not going to get into the details of this, but we know that we have measured things, and we know roughly that this is consistent, except there is a small things which I will discuss. Fine. Now, what happens to these photons? These are basically the ambient photons, which is there, and which is what we now see, and which has been now measured, and very well. So this was the first measurement of the cosmic microwave background by Penzias and Wilson, which is basically measured here. This was at 1965, and because of which the first evidence of Big Bang came, and they got the Nobel Prize in 1970. And after that, people have measured this cosmic microwave background at very high precisions. Kobe measured it much later. So that is basically, this is the plot of Kobe in the gigahertz frequencies. And this basically very well predicted that there should be a black body of 2.73 Kelvin. And this is what we now know that this is actually true. And this basically nailed that the Big Bang theory is right. Fine. And we have still went ahead, and we have measured these CMB photons much better, and we have got very good understanding of the universe. And for that, the reason Mather and Smoot, which is basically, this is the prediction, what they got as an instrument with the Kobe, and they got the Nobel Prize in 2006. Okay, fine. So I have now said that everything the predictions of the Big Bang theory is consistent with observations, and we think that everything is right. So then why are we sitting here? We should close the shop, and then we should not worry about it. Okay, so that is where things start coming interesting, and which is now I'm referring it as an Epoch 5, which is the accelerating epoch. Okay, now the success of the FLRW model comes with a price. Okay, so the price is that this is the pie cake of the universe. This is basically, if 100%, let us take 100 of them, is basically is the universe content of the energy density. Now, what we are made up of, and what we see as galaxies, photons, and this, it only makes up only 5% of it. Right? If you want to explain all the observations currently, including the cosmic microwave background observations of Planck, WMAP, and everything, they can only be explained if the atomic matter, which is basically made up of us, the Earth, the galaxies, and the photons, they make up only 5% of it. The rest, 95%, is dominated by two kind of entities. One is referred to as dark matter. Other one is referred to as a dark energy. Fine. Now, so the question is, Okay, so you have told us that, okay, so we are able to explain it. So then the question is, what is dark matter and what is dark energy? Okay, but the most puzzling of it is that we have actually absolutely very little information. I can even say that we have zero information about dark matter or dark energy, but we know its properties. Please understand, it's not that we don't know the properties, but we don't know what is it content, why is it like this. All those information which as a physicist or as a scientist which we will be interested in, we don't know about it. Okay, so basically the FLRW model, which is the Big Bang model, is a very good model, but of course it cannot explain the supernova observations. I've not gone into this, but later on, if I have time, I will discuss it. And all the CMB cosmic microwave background observations, they can only be explained is if the universe is dominated by two entities, which is one is called the dark matter and one is called the dark energy. And the problem is that we have very little information, absolutely no information about dark matter and dark energy, but we have lots of observational evidence which says that this should exist. Right? Okay. So now I'm coming back to this. So basically what I'm trying to say is that we are looking at the universe in like how the blind men were looking at the elephant, and we are seeing patches of things. Okay. And from this we are saying that this is true, this should be true, this should be true, but we have really no complete information about the elephant. The elephant here is basically the universe. Fine. So I want to just now go down and understand the two components which I mentioned. One is what is called the dark matter, and the other one is what is referred to as the dark energy. So I will briefly elaborate on these two things, and then I will end my talk. Okay. So what is dark matter? So the dark matter is an entity which neither absorbs or emits detectable amounts of light. So when I say detectable amounts of light, it basically, from the current observations, what we can say is that it actually doesn't interact with light. But of course, it might be actually very weakly interacting, so hence we don't detect it. That is also possible. But in the current understanding is that it actually doesn't detect, it doesn't interact with it. So, but how do we know that it exists? Because it has mass, and Einstein says that anything which has a mass or which has energy will interact with gravity. So how do we know it? So what people have done is, this has been going on for the last 100 years or so. And what is this? This is basically the plot, a schematic plot of the velocity of the of various galaxies. For instance, they've plotted. Okay, so let us go back. So this is the plot of the rotational velocity of various stars in a galaxy and their distance from the galaxy, from the center. So for instance, people have been plotting various of these stars, the various stars which are going around the galaxy. For us in our galaxy, you ask a question, what is the, you can measure the distance from the center, and you can calculate what is the what is the velocity by using the spectrometer. So, and then you plot this, calculate the velocity and plot the distance, and you plot it. And the white curve is basically what is the measured plot, and this is what is the calculated. So why I'm saying this is this? So basically we can calculate this by just by going to the Newtonian physics, and we know that this is true. V squared is equal to gm by r, where m is the total mass within the radius, and we don't see any stars beyond this point. So after this point, is actually what you expect is that till the masses are there, till the stars are there, we assume these are the masses. And if you take this mass and you calculate, then what you see is that then the profile of these stars in these galaxies should go like this. However, what you see is that this actually doesn't go away. It actually keeps going, and it's a plateau at some point and then just saturates. Right? So the only way, if this is true, for instance, if the Newtonian physics, even gravity, GR is true, then this should then there should be a mass. There's a missing mass, and this missing mass is what is referred to as the dark matter. So of course we don't see this. We don't see this because it doesn't interact with light, or it very weakly interacts it. So but the most interesting thing is that this dark matter, what we call it as dark matter, because we don't see them, that's where it is not visible. It is 10 times the mass of the galaxies, 10 times the mass of the stars. So if I say that if all the stars masses, let us take 10 and 10 grams for instance, then the dark matter should have 100 grams of it. So basically, most of it is actually contributing, the mass to the galaxy is actually contributed by dark matter, not the visible not the visible stars. Fine. So this is the dark matter. So now let us see how do we know that what is dark energy? Now, so the thing is, we already dark matter is strange, but the dark energy is even more strange. So to explain what is dark energy, so I am going to take a simple example. So let us take, I have a box of gas inside a container, and how do we know that there is a gas? Because because there is a pressure, because I cannot keep pushing it inside, because after that it will, if I push it, then it might actually break the container. So how do we know that? Because we know that physically we know that it is because the pressure is basically obtained by the collisions. Basically, the particles won't collide on the container's wall, and hence you will have this. Now, if I increase the number of gas molecules, the number of collisions will increase, hence the pressure will increase. Now the thing is, dark energy, it's actually pretty mysterious. We don't understand why it is like this, but we know the properties should be like this. The pressure of the dark energy is actually negative. So if we increase the number of dark energy molecules, the pressure actually decreases. It's opposite. So in the earlier case, for instance, if I had an oxygen molecule in this thing, if I keep putting more and more, then the pressure will increase. But here it is actually opposite. It actually is it's opposite to what we experience in the day-to-day life. So if you keep increasing the number of particles, the dark energy molecules, for instance, then the pressure actually decreases. We don't see this. This is an artistic impression. This is just to illustrate that what this basically is. So unlike the matter, the total energy in the dark energy is proportional to the volume of the empty space. So basically, it just keeps increasing as the universe expands. Its energy also keeps increasing. It's completely contrary to what we have. If the universe expands, the energy density of matter and the radiation, like photons, should decrease, which is actually opposite. So what is happening is that because of this mysterious nature of dark energy, our universe is actually accelerating, and that is what is happening currently. So the current phase, so this is basically the Nobel Prize of Rees and et al. So what they did is they mapped the galaxies to very large distances, and they plotted as a function of what is referred to as the luminosity as a function of redshift. Basically, they just mapped the luminosity as a function of redshift. What they found is that if this is matching with the observed data, this is the observed data. All these are black and red. Now, this is the 1997-98 data. The current data is even more better. So, but I have not plotted it because of the lack of time. But if you see this, the only model which can actually fit is basically what is there in the green line, which is the total the dark energy. That time is 69, but now we know that it is 65 because of the errors that time. So the most of the content should be dark energy, which will be 65, which is like 65%. And this omega m also includes dark matter and the normal matter. So it is basically the total matter. So, and they were given a Nobel Prize, Rees et al. Were given a Nobel Prize in 2011 for their astonishing discovery of the accelerator. So, so the thing is, now this poses us the interesting question. So, as I mentioned, let us go back to the pie diagram. 69% of it and 25% of dark matter. We don't understand it well. Now we only understand 5% of the dark atomic matter. So the question which now poses is, what is true? Whether is this dark energy is basically realistic? Because whatever properties I've mentioned, it looks very unrealistic. So what people have been looking at is basically, is there something wrong with the general theory of relativity? Maybe general theory of relativity is reasonably good for many experiments. But for the largest possible scales, in the largest possible scales in the universe, maybe the general theory of relativity may be wrong. So maybe this Einstein's equation may be partially correct to a certain extent, but one has to, it may be wrong at the largest possible scales. And people have been looking at modifications to this. So people have been proposing models. And in the next in the next 10 years, people were saying that if some of these can be observed in the next uh, set of cosmological observations, and they may actually prove or disprove whether general theory of relativity is right at the largest possible scales, or dark energy is right, or any other model is right. Fine. And I'll take one more slide, and then after that I'll finish. So the most serious issue right now, which the cosmology is facing, if you remember, I mentioned something called the Hubble constant. The Hubble constant is basically the current value of the Hubble parameter. Now, that is a very important parameter because that tells you what is the age of the universe. Now, different measurements. What is happening is that two sets of measurements are giving two different set of values. More importantly, the set of measurements from CMB and the supernova measurement, which tells us that why the dark energy exists. CMB also tells us the dark energy exists. These two gives us very, very different values of Hg. So that tells us that we are missing out something very crucial. And people have been saying that this tells us pointed that there is a problem with the current model, which is what's called the lambda CDM model of the universe, or the FLRW model of the universe. So people are trying to figure it out, what are the problems. And of course, there are no solutions yet, because this has been going on for the last 5 years. And people think that H0 tension, which is now referred to as H0 tension, will tell us that whether there is a serious problem with the current understanding of cosmology. So again, I want to mention this, saying that our perception is limited. We can only see part of the universe, and from this we are conjecturing that the entire thing has to be an elephant, which we don't know whether it is true. But it is, in general, we have to think about this when we are doing measurements for the universe. We have to think that we are only looking at part of it, and every time we have to check with others and use that, and then come up with the model of the universe, which is the elephant in this picture. Okay, so I will wind up with this slide. So the standard model of cosmology has been successful. However, it comes with a price. The universe consists of close to 95% of the unknown matter and energy. We need lots of our observations to understand what is the problem in our understanding. And the exotic matter or modifications to gravity will only come in the next 10 years or so, because that's when we are expecting that much more refined observations are going to come. But this is actually an exciting time for students, because these are fundamental problems in physics. And if anybody can take a shot, because nobody knows many things well, so anybody can take a shot at it, of course, with a very good knowledge of background physics and mathematics. So then it's an exciting time. Thank you very much.
Thank you so much, sir, for sharing such brilliant presentation, and also the way you explain in a chronological order by dividing it into the various epoch. So I think a student might get the clarity on the topic we were discussing today. Now we'll open the discussion for some questions. If you have any doubt or questions or anything you would like to comment on today's topic we were discussing, any point, please feel free to drop it in the chat box, and we'll be highlighting those questions so that sir can answer that. Please do that, because we are already 1 hour we cross it. We really don't want to take the video longer, because then it will take longer time to get it into the YouTube. So please feel free to ask it. And Mevish Afia, you have mentioned one question. I please specify it, because I won't be able to connect that question, because it is then how the global warming cause of higher temperature, in which context you were asking this. Please mention that so that I can take that question. So we'll be waiting for some time for some question, and then we'll wind up today's discussion.
This video will also be available on the Nehru Planetarium YouTube handle. In case anyone wants to refer it for the later references, feel free to do that. So I think we are not getting any question in the comment,
Okay.
and still people are watching it. So if there is no question, we can wind up today's discussion. All right. So no
I can
question.
stop
Thank
sharing.
you. Yes, you can stop sharing.
Yeah.
Thank you, everyone. Thank you for giving your precious time for coming online and attending this session. Planetarium, thank you for your all active support you have given in this last few time when we decided to come online and have this interaction with the expert on the various topic we were trying to get them on board. And thank you, Professor Narayan, Shankaranarayanan sir, for giving your time to explain this topic such beautifully and elaboratively. We really hope to host such informative session in future as well with you.
Thank you very much.
Thank you. Thank you so much, sir.
Thank you very much. Thank you.
Thank you, everyone. Have a nice day.